Hello everyone, the following is the second in a series of lectures covering Chapter 40. Today we'll be talking about the photoelectric effect. We already seen how blackbody radiation was modeled with a quantum model of particles, and if you try to model it with classical physics, you would fail to do it. You basically could not explain what was observed when the peak intensity was in the visible range when classical physics would expect intensity to peak to at lower frequencies. There was something else, again, in the end of the 19th century, another experiment you could do, which couldn't quite be explained with classical physics. This was the photoelectric effect. Basically, the idea was that if you heated an object, it would glow. If you heat an iron, it glows, right? And essentially saying that solid objects, solid matter, can effectively emit light if they're hot enough. That's just what we learned with thermal radiation. We always emit radiation. The hotter we are, the higher frequency the radiation is, which is why we normally emit infrared radiation, and eventually, if objects get hotter, emit visible light, and so on. So, the question was, well, if a hot object can emit light, is it possible for light to emit particles? So what physicists set up was something that's summarized. So this lab setup we show here is like a sort of like general outline of what physicists were experimenting with. But what they were basically doing was shining light into a plate to eject electrons. And they observed that, yeah, in certain setups you could see that happening. Now, obviously, you can't see electrons getting ejected out of the plate, but the way that the general setup worked was you would get a vacuum chamber where no light would enter unless you wanted it to. In that chamber, you have two plates. One's negatively charged here, one will be positively charged by default. And there's also a variable power supply, a voltmeter here to basically measure and adjust the potential difference for the plates. So the difference of the plates was tuned by the battery. So the battery is essentially what determines the potential difference. But again, by default, they were setting it up so that this plate here will be the negatively charged plate. And also, you have an ammeter in your circuit here to measure current. So they found out that you could shine light into plates and electrons will get emitted out. And then you'd see then that electrons would reach the other plate called the collector plate in the textbook. And in doing so, they would then travel through the circuit back to the original plate. And so you would register a current. These electrons, since were ejected from the plates due to incident light being shown on them, were called photoelectrons. Now, because you can increase the potential difference across the two plates, what that does is once you have light shining on the ejecting plate and effectively ejecting photoelectrons out into the space between the plates and the vacuum chamber, increasing the potential difference by increasing the voltage supplied by the battery will essentially give all the ejected electrons a push towards the collecting plate. And that means that normally, electrons that could get ejected by the incident light did not necessarily reach the other plate. But by increasing the voltage, you could make sure that all ejected electrons do reach the other end. In doing so, then there will be more a faster rate of electrons going through the circuit, and so you measure a larger current. Eventually, though, the potential is so large that it doesn't really affect the current anymore, since at some point all the ejected electrons do reach the other plate. So increasing the potential difference doesn't have any effect past that point. There was another thing you could do, though, while observing this photoelectric effect, which was to reverse the polarity of the battery. So now the plate that the electrons are getting ejected from are it's a positively it's a positively charged plate, and the collection plate on the other side of the vacuum chamber is negatively charged. So this creates a negative potential difference. This means that ejected electrons have to spend their energy to get to the other side. This will mean that as you increase the potential difference to bigger negative potential, less and less of the ejected electrons could reach the other end. Eventually, the potential difference was so negative that no electron could get to the collecting plate, and so you would stop measuring any current through the circuit. You can see the graph here showing you how, as you vary the voltage of the battery, how the current changes. And effectively, right, it doesn't take much to saturate the current at higher voltages. The current basically reaches a plateau. What determines the sort of amount of current is the intensity of the light. So high intensity lights would eject photoelectrons at a faster rate, so you'd see more current. Now, the ejections that get ejected all carry different energies as they travel to the collecting plate. But effectively, by reversing the polarity, you could find a potential that was strong enough to stop all electrons from reaching the other plate. Effectively, this is like building a hill that's big enough that all the you're maybe trying to, like, I don't know, throw something up on the hill, but eventually the hill is so tall that you can't get anything up there. So you could actually then, by sort of modulating the negative potential on the battery until all current stop, you could then determine what the maximum kinetic energy of the electrons was, because that would be the point where no electron can reach the other plate. So this whole phenomenon of the photoelectric effect of this experiment, to explain why light could eject electrons, it could be somewhat explained with the classical model, but not entirely. So classical physics that thinks of light as, similar to mechanical waves, would have thought that if you increase the intensity of the light shining on the plate, that would provide the ejected electrons with more energy, and therefore, right, you will need like a bigger stopping potential. You will need a taller hill to stop all electrons from reaching the plate. They eventually find out that that wasn't the case. Intensity did not factor in to the energy of the ejected electrons. In focusing in the whole idea of light being a similar to a mechanical wave, whatever expectations physicists had about this photoelectric experiment did not meet what they observed. So they couldn't explain what they saw with classical physics. So let's look at what they saw versus what they predicted. So they thought that, it didn't really matter what the frequency of the incident light was, since frequency did not really factor into the energy of light when seen as a wave, really. Then, but what actually happened was that if they were shooting light at the plates that was low frequency, the no current will be detected, so no photoelectrons were getting ejected. So it seems like there was like a cutoff. There was a threshold frequency which below that you will get no current. Also, they expected that as increased intensity of light, since light, thinking it's a wave, starts to cook the electrons, starts to build up more energy in the electrons, and so the electrons accumulate more energy and then shoot out. But it turns out that more intense light did not determine the energy of the electrons. Thirdly, they thought that frequency is just a property of the wave. It's based on how the wave is initially set up. It doesn't tell you anything. It's not related to the energy of light, so they should not factor in to how much light the photoelectrons get from, sorry, how much energy the photoelectrons get based on the frequency of the light. But it turns out that as they increase the frequency of the incident light, it will also increase the maximum kinetic energy of the photoelectrons. They also predicted that it would take some time from when you turn on the lamp to the electrons getting ejected. So it would take some time between you shining a light on the plates and you reading a current. This was the idea that since if light classically is behaving as a wave, then it will start transmitting energy over some time to the electrons. The electrons will start getting like more and more energy until eventually they have enough energy to escape the metal, and at that time then they escape, and then you see a current. It's kind of like microwaving popcorn. They thought it was like that. Basically, right, microwave popcorn doesn't pop right away. You put it in for like a minute, and 30 seconds in, you start hearing the pop. The kernel's got enough heat to actually start popping. They thought electrons were doing the same thing. That was not reality. As soon as you turn on the light, electrons, you saw a current right away. Seems like electron ejection was instantaneous, even at low intensities. So it seemed like frequency was a factor, intensity was not. Reality is often disappointing, or perhaps classical mechanics is often disappointing. Okay, so yeah, what was being observed did not meet the expectations. It wasn't until 1905 when Einstein, working off Max Planck's work on black body radiation, kept developing that idea. He was able to publish a paper that explained the photoelectric effect. This was actually the only theory he had which earned him a Nobel Prize. Basically, much like Planck was saying, the theory says that light exists as quantized bundles of energy called photons, and their energy is proportional to this frequency that they have. In fact, it's equal to this Planck's constant times the frequency, and the speed of these photons is effectively the speed of light, at least in a vacuum. So this model sees light as having particle properties in the form of photons. And the way that they interact with electrons is that they're absorbed instantly. Once light reaches the plate, the photons that make up the light are sucked up by the electrons right away. And the absorption happens instantly, and the electron either gets enough energy from a photon to leave the plate, or all that energy just gets lost. It's possible that perhaps two photons will arrive and the electron will absorb them at the same time, get double the energy, but the more likely scenario is that it's just one photon getting absorbed by one electron. And again, so overall, these are one-on-one interactions. And also, because they're interacting with absorbing one photon at a time and then ditching that energy or using it to escape, that means that they need to get enough energy from a single photon to escape, which means that the energy they get from the photons has to be bigger than the work function, which is whatever energy they need to detach themselves from the plate. So whatever energy they have left over after overcoming the work function goes into their kinetic energy. So the max kinetic energy of a photoelectron is all the energy it gets from absorbing a photon, that's h times f, minus the energy spent in overcoming the plate's binding energy. So that's a work function phi. So the idea is that whatever energy is left over after the absorption, after overcoming the work function, goes into kinetic energy. But again, for this ejection to happen, the photons need to have enough energy to give it to the electron that it's big enough that it overcomes the work function. So the intensity of the light doesn't matter. Intensity just means that there's more photons reaching the plate. What matters is the frequency of the photons, because that determines their energy. And also here's a list of work functions for different metals. Now, we can explain what we observed in the photoelectric effect by using this quantum model developed by Einstein. The fact that kinetic energy depended not on intensity but on frequency is explained by saying that, yeah, the energy electrons get come from the energy of the photons that depends on their frequency, not the intensity. The fact that electrons were being emitted instantly was explained by the fact that the interaction between electrons and photons is instant. Also, the fact that below a certain frequency for light, you'd see no current was explained by the fact that since interactions happen one at a time, only photons with enough frequency, with enough energy, could be able to overcome the work function. So there was a threshold in frequency. And also the fact that as you increase the frequency of the incident light, the maximum kinetic energy also increases. Makes sense because, again, more frequency photons means more energy they give to electrons, and thus the electrons has more kinetic energy. So then overall, then you could actually derive from this what the lowest possible frequency of light is needed to generate a current. That's a cutoff frequency. And then obeying the wave formula, right, that C is equal to lambda f, you can find the cutoff wavelength for the photons. So it seems that still, even in this photon model where you're considering light as particles, there's a notion of photons having frequency and having wavelength, which are properties of waves. So even at this juncture, we're seeing how, even by considering light as a particle, there's still wave properties to it. So we can't really think of it as a particle exclusively as we've done with normal particles in classical mechanics. Anyways, what we're showing here on the graph on the right is different metals that have different work functions. And to show you how, as you increase the frequency of the light incident on the plates, the kinetic energy increases linearly for the photoelectrons. But obviously, the threshold frequency is larger for metals with a higher work function. In the next few slides, we have a few examples of modern devices like charge couple devices that take advantage of the photoelectric effect for building telescopes or modern cameras. So you can pause the video if you want to learn a bit more about them. They are supplementary for the purposes of assessment. So a few quick quizzes this way. This one says, okay, you're sitting outdoors and you're exposed to all kinds of radiations just by being in your own garden. And just want to rank them based on the energy. And again, in reality, predicted by the quantum model, the energy of light is just dependent on their frequency. So higher frequency radiation is more energetic. So from all the radiation listed here, the most high frequency one would be yellow light, followed by probably microwaves, then FM radio waves, and AM radio waves, since AM has the longest wavelengths of them all, also has the shortest frequency. So sodium light is the most energetic light. In this one, we're basically doing the photoelectric effect lab, and we're basically asking what happens to the stopping potential if we increase the frequency of the incident light. So again, the stopping potential is when you reverse the polarity and you make the potential so strong that all electrons get repelled, so you see no current. If you increase the frequency of light, you are also going to increase the kinetic energy of the photoelectrons. So you're going to need a bigger stopping potential to stop those electrons. So the stopping potential would then be even more negative, so it should move to the left. And in this question, we're basically asking, what if we plot the kinetic energy as a function of frequency if we follow the ideas of light as a mechanical wave? If we do that, then we see that, right, we predict that the frequency of the light has no effect on the energy of the photoelectrons. What would make a difference, though, is intensity of light, because a higher intensity light would, in quotation marks, cook the electrons faster to to more give it more energy, and thus they move faster out of the plate. Then a few examples here from the textbook asking you to find the maximum kinetic energy for a sodium plate. So again, you can use the work function formula here. Again, all it's saying is whatever kinetic energy you have is the leftover energy from the photon after you spend some of that energy in overcoming the work function of the metal. And then the cutoff wavelength, and it's just finding out what the lowest possible frequency or highest wavelength is before photoelectrons stop getting emitted. Anyways, that's all for now. So I hope you join me next time where we'll be talking some more about quantum physics.